अथर्व, मानसी, ऋतुजा, मिताली, रुपेश, अविनाश, कीर्ति, वसुधाचल, दुर्वेश, मयूर, ईश्वरी, प्रवीण, देवेश, देवर्षि, प्रज्वाली, प्राची, आशुतोष, स्मिता, गणेश, मैत्री, रसिका, युगा, अनुजा, पूजा, and Prachi Pandey. Prachi Pandey, I think it's double. Yeah, it's double number. It's double. Prachi Pandey, and then this is Sheetal Market, Yuga. Once again, Yuga. I am not audible. Okay, okay. I don't know what has happened. I'll just what the problem is. Am I audible now? Am I audible now? Okay, am I audible now? Some students say I'm not audible. Some students say Anjali Kumari says I'm not audible. Can you hear me now? Can you hear me now? Uh, okay, we'll try again. Am I audible now? This is, I'm wearing my plugs. I'm wearing my plugs. Am I audible now properly? With my plugs, right? Okay, if I'm not audible, again, you can just post a comment on that. Maybe some connectivity issues or anything like similar to that as such. Fine, it seems now I am audible. So, fine, fine. Thank you, Mayur. Thank you, Anjali. Pooja, thank you. Sakshi, thank you. Aditi, good morning. Arshada, good morning. Once again, a very happy new year. Let us hope it would be a better year as compared to the last year. If you remember last year's last lecture, we finished with the theory of isostacy. And this was, see, when we spoke about the Wegener's theory, when we spoke about plate tectonics, okay, these were horizontal movements of these so-called lithospheric plates as such. And as far as the isostatic theory was concerned, it is an up and down movement of the same thing. Akshata says my voice is low. Should have been. I'll just check. Okay, now again I'm not audible. There is a lot of confusion. Some students say I am audible, some students say I'm not audible. It could be possibly because of the it could be possibly because of the battery here. Okay, I'll just check my battery levels. Of my this thing. I'll just disconnect. Okay, have disconnected and I've connected again now, right now. So am I audible now? Now. Am I audible now? Oh God, what is this problem? Okay. Uh, I've removed my earbuds now. Am I audible properly? Mm, let me know if I'm audible now. I've removed my and switched off my earbuds. I don't know why my volume should be less as such. I'll try to speak louder. Let us see if that can cover up with the what's voice is a bit low, sir. Oh, I'll try to check my audio on StreamYard. Okay, okay, fine. It seems to be proper now. Some problem, some issue maybe with the microphones of the. Let us see. Let us see. Okay, thank you. It seems that I am appreciably audible, may not be clear as the earlier lectures, but it seems I am appreciably audible. So let us start with this. We spoke about these theories of crustal formation. Two of those theories, thank you, Durvish. Two of these theories were horizontal movements, and one of the theory that is the isostasy, that's the theory of buoyancy, which actually we did say the last time also that it's not a geographical theory. It's physics and mathematics being used to explain a geographical process now. So that is what we, thank you, we have been doing last time. Now, from the continental scale, just give me a second. One of the phones was ringing, so I had to switch it off. Um, yeah, from a scale, from a continental scale, or I would say from a a scale of the lithospheric scale. Let us come down to a smaller scale. Let us zoom down into the smaller aspects of the crust. And what I mean here is we are supposed to be doing rocks as such. Yes, we are yet to do. We have not done. Uh, uh, by the way, as far as the theories of crustal formation are concerned, we have finished with the third topic. In the second topic, we are left with earthquakes, volcanoes, and of course folding and faulting. And of the first topic, I remember hypsometric curve is remaining, but in sequence, see, it's either way. We could go back there, or since we are continuing with it, let me take it up further and let us understand the rocks, and then we'll go back to how these rocks crumple around faulting and folding and so on and so forth. The presentation that I'm going to make today is basically a presentation that I had prepared for. Oh, just a moment. Yeah, it's a presentation that I had prepared for. Okay, this is a presentation that I had prepared for a lecture that I was supposed to be delivering for UPSC aspirants. I will cut out the so to say the technical and the very deeper aspects of it, and I will make it simple to understand for students of first year undergrad level as such. So let us move on with that, and let me take up the first. I'm running this live on YouTube as my slide share. I don't know whether I've spoken about this to you all, but as far as SlideShare is concerned, it is a site where you would be in a position to have various PPTs, and I have donated a few of my PPTs on the SlideShare as well. So you can search for my PPTs on SlideShare also. Um, I have put up the theory, the PPT on rocks, and then this is followed by weathering, and then I have one more about mass movement, and then one exclusively for Himalayas, and so on and so forth. So those interested could just visit that and go into the details of understanding that. This is something that we started with, isn't it? The interior of the Earth, and you'll see that you can understand the proportionate sizes. Okay, why is it that the crust is so much dynamic? It's because of the fact that the crust is so very narrow, and comparatively, you'll see that the mantle is thicker, and the core, that's the inner core as well as the outer core, is significantly thick as such. So possibly one of the reasons why the crust moves so much is the comparative thickness that you see as far as the layers of the earth is concerned as such. Okay, these are the geological provinces, I would say. I would not be able to enlarge this, unfortunately, because I'm running this from from the live website as such. But okay, let me just take you through. The first one here, it reads shields. Okay, shield is basically the first of those rocks which came up on the surface of this particular planet as such. And you'll see that you have a larger part of this shield in Africa. This is called as the African shield. You have the Indian shield here. Okay, you'll have the um, Indian shield here, and you have the Brazilian shield here. Okay, then you have the North American, which is also called as the Canadian shield, because it involves a lot of part of Canada as such. And then you have the European, the Siberian, and of course you have the Indian shield also. The smallest of them is the Indian shield as such. Then you'll see that as far as the other parts are concerned, let us not go into the other parts as such, but say the next of the slides to come is a few quotations with regards rocks as such. Okay, landscape is a function of structure, process, and time. The very most famous, I would say, coming to us by given to us by Davis as such. A rock should be conceived as as a product of its environment. Okay, because you'll see that the same rock could look and appear different in different types of environment. The same thing in equatorial region could be different as far as the monsoon is concerned, and you go to the deserts, it could be different. So the statement is very interesting. A rock should be conceived as a part of its environment. Then rocks are the books of the earth's history, and fossils are their pages. Okay, that's very interesting again. Rocks are the books of history of Earth's history, and fossils are their pages. You read rocks through their pages. Now, this could be a bit dicey, basically, because fossils, where we say they are the pages of the reading the Earth's history, fossils are found only in the sedimentary rocks. You will not find fossils in igneous rocks. So a bit dicey, I would say, but nevertheless, fine to bring up an interest in the topic as such. Then rocks constitute the manuscripts of past Earth's history on one hand, and basis of contemporary scenery on the other. Okay, you'll see that in the background you see those beautiful two boulders which are standing, huge in size. Okay, they are contemporary scenery, but you go into the learnings of that, you could understand different aspects within rocks there as well. I don't remember if we have done this earlier as such, but when we divide the Earth into the Earth's crust and the entire Earth as such, this is the sequencing. Now, we may have done this, but it's interesting to do it again here at this point of time, because when we did it earlier, we generalized it, and now we are going to associate it with a lot of things that are associated with rocks as such. So when we're speaking about the entire Earth, okay, iron, oxygen, and magnesium, iron, oxygen, silicon, and magnesium. Okay, these four elements, they account for how much? You'll see that they will account for 30 plus 30, 60, 65, 70, 80, 93% of the entire Earth is made up of iron, oxygen, silicon, and magnesium. So, an interesting aspect, let me tell you, as science students, we should be, and students who have learned their chemistry should be logically able to understand that these are the say the elements that we should be finding in the rocks also. But before we conclude that these should be the elements that we should be finding in the rock, the surface of the earth is does not churn out of the entire earth, isn't it? It's the upper mantle and the crust which churn up. So it's interesting to know what the earth's crust is made up of. And when we move to the crust as such, you'll see that oxygen, which was number two and at 30% for the entire earth, comes to number one, and it makes up half of the earth's crust, 47% of it. Silica is 28%. So 50 and 30, 80% of the Earth's surface is going to be made up of oxygen and silica, and you add another 8% and of aluminium and iron, you'll see that again it comes to 95%. So this can be logically concluded that most of the rocks will have oxygen, silicon, aluminium, iron, and to some extent magnesium as such. Okay, so it is these elements which we need to look into when we are looking into the various types of um, rocks as such. Okay, now when we are looking at say the various aspects, say, living, when we look at these constituents, different types of constituents. Say for example, we just spoke about the solid earth. Okay, we said that it's 5%. Solider, it's 5% oxygen, silicon is 28% silica. I believe this is the top, the crust. Instead of solid earth, I believe they mean the crust, because it reads oxygen as 47% and silicon as 28%. Okay, the percentages are a bit here and there, but then they match to what we were saying. Atmosphere, you'll see that 78% of nitrogen, 21% of oxygen, and 1% of argon is what we're going to have. As far as the oceans are concerned, we need to understand that they have 86% of oxygen. Magnesium is just 0.5%, sulfur is 0.5%, chlorine is 2%, and hydrogen is 11% as such. And as compared to all these things, living matter is made up of carbon, oxygen, hydrogen, nitrogen, calcium, and phosphorus. Okay, so you'll see that oxygen is a very important component. Either it could be the crust or atmosphere or oceans or living things as such. Had these percentages been different, would we have had life? Possibly we would have still have had life on this planet, but then the the characteristics, okay, the shape and the structure, the composition of the living organisms could be changing. In fact, you'll see that throughout the geological history also, we see that as the gaseous components have changed, say the climate on the surface of the earth has changed, and this change has brought about changes from very large sized plants in the Carboniferous, that's in the Paleozoic, to large sized animals in the Mesozoic, and then the smaller sized animals and advanced animals in the form of mammals as far as Cenozoic is concerned. So this is how we need to connect, say pure sciences like chemistry and physics and biology to application-oriented subject like physical geography as such, and that's why this tends to get important as such. Then, are we basically classify rocks on the surface of this particular planet in a few ways, and this includes say the three major types based on the composition, and that's say the igneous rocks, the sedimentary rocks, and metamorphic. We are going to go into the details of each of them, and let me tell you that they are interchangeable. Now, what does interchangeable mean? I think we are missing out on. I'll just take you back to the smaller aspect of it here. Okay, I don't know how I should be pasting, or tomorrow I'll get the original of this and we'll speak about that. But then igneous rocks. Okay, you're going to have igneous rocks, and we have the sedimentary rocks, and of course you have the metamorphic rocks down here. When we speak about these rocks as such, how do they interchange into each other? You'll see that igneous rocks are also called as primary rocks because they emerge out of volcanic activity. When these get eroded, when they get eroded as such, okay, when igneous rocks get eroded as such, they will get this eroded material will get deposited in layers, and that is why sedimentary rocks are in the form of layers as such. Okay, sedimentary rocks could get eroded and go into what are called as secondary sedimentary rocks. Or you'll see that when we spoke about plate tectonics, igneous rocks, sedimentary rocks, or metamorphic rocks could go into, say they could slide into each other. Okay, that's the margins of the plates. And as they go down, they would melt, and igneous rocks could come back as igneous rocks, but sedimentary rocks will come back as new igneous rocks. Metamorphic rocks will also come back as new igneous rocks as such. These are primary rocks. These are called as secondary rocks. And metamorphic rocks are called as transformed rocks. How do they get transformed? They get transformed because of pressure and heat. Heat will make them melt, and you'll see that this will give you a completely different type of rock. Say, for example, limestone. When it is pressurized as such, it leads to formation of marble. Okay, so a completely different rock may be formed as far as uh, a metamorphic rock is concerned. So, and as I said, that from igneous towards sedimentary is due to erosion. From igneous towards metamorphic is due to pressure and heat and pressure. Okay. Now, from sedimentary to igneous is because of melting. From sedimentary to metamorphic is again heat and pressure. From metamorphic to igneous is melting and volcanic eruption, and metamorphic to sedimentary is again erosion of this. See this erosion and then deposition and consolidation to form sedimentary rock. So every form of rock that you see on the planet today will belong to either of these three categories, and they keep on moving into these cycles. How long these cycles run? Of course, they are going to run in millions of years. If they are going to move from one stage to the other, and so on and so forth. As such. So that is the cycle, rock cycle as such. What are the key identifying features that we should be looking into these respective rocks as such? In igneous rocks, okay, in igneous rocks, we tend to look at holes created by a tapped gas. You can say that when the magma, it comes up and it blows up like lava. Okay, you'll see that this lava is going to fall somewhere. When it falls somewhere, or even at the time when it is emerging in the form of magma, there could be gas, okay, because it's very high temperature, and these temperatures are resulting into a lot of chemical activity. This could yield a lot of gases as such. Sometimes these gases escape, sometimes these gases do not escape as such. As a consequence, they form holes. Okay, these are called as gas bubbles as such. So a primary way, if you know that it is igneous, the next thing that you are going to look at is whether you're going to have gas bubbles in that. If you have gas bubbles, you start classifying it in a typical way. Then you have a glassy surface. Within igneous, you have glassy surface. Okay, sometimes you'll see that they are shiny, smooth surface with this forms from quick cooling, because some rocks you'll see that they could be formed under water surfaces, which is already the water temperatures are low. So when the hot magma comes in contact with the water, it will quickly cool down as such. So such cooling will yield you shiny, smoothie surface materials as such. And then you have crystals, okay, like small flat surfaces that are shiny or sparkles, as such. Okay, so all these categorize in igneous rocks as such. Sedimentary rocks, you'll see you will have sand or pebbles. Okay, you could have individual stones, pebbles, or sand grains visible in the rock. And another thing that you will find, as I said earlier, also that we find fossils and in the form of imprints of shells or insects or leaves or bones of larger animals as such. You will find them in sedimentary rocks as such. The earlier point, sand or pebbles or rocks, you'll see that from a very small particle of soil or clay, okay, this particle, the diameter of the particle keeps on increasing, and it is the sequence in which you name these small particles, in the sense from sand to a larger one is a pebble, and then a stone, and of course a rock, and so on and so forth. Sedimentary rocks are going to be full of these. And metamorphic rocks, okay, you'll see that they are ribbon like. Okay, you'll see that they're not going to flat and straight, because there's going to be a lot of pressuring. Because of the pressure, there will be wavy or straight stripes. Okay, or you'll see that many a times, because of the heat also, you'll see that it makes the material flow here and there as such, and that's why you'll find straight or stripy ribbon bands on the colors of these rocks as such. So these are key identifying features as far as rocks are concerned. So you'll see that this now, what should this be? Okay, you'll see that obviously you have a lot of gaps in this. Okay, and this could be easily identified as a igneous rocks. Okay, you'll see that you have a large blob of emptiness in between. This is possibly because of the fact that a large bubble of air got trapped in this, and then it slowly escaped. Now, it may have escaped from this vent here. Okay, so it has kept itself space to move. Now, we are not absolutely sure. Okay, because see, photographs of rocks could be very deceptive, but on the face of it, it may so have happened that initially it was the air was blocked in here. Eventually, the air pressurized to such an extent that it had to find its way out. By that time, say majority of the surroundings had solidified, and gradually it found a very small edge through which it could just seep out, leaving behind a huge hollow or a huge bubble that eventually got carved out as far as this igneous material is concerned as such. Okay. Before we go into understanding the igneous rocks as such, let me also tell you all that when we speak about these rocks as such, um, what are rocks? Rocks are basically consolidations of minerals. What are minerals? You'll see that minerals are nothing but different compounds. Where do they form from? They form from elements. Okay, now you'll see that when you move from geography to science, you slowly get into the terminology of science. So chemistry starts with an element. Okay, and we have seen that the four major elements that you would find on in the surface, we've seen this earlier also, that the four major elements that you're going to find in the surface are going to be oxygen, silicon, aluminum, and iron as such. So it is very obvious that you would be finding this material. Okay, but they form out of various elements. So you're going to have elements which are going to come together, and they are going to form minerals as such. And you'll see that groups of minerals will organize themselves to form rocks as such. So rocks is an end product of elements moving into or say chemically acting into compounds, and different compounds divided into different groups are going to be called as mineral groups. And when they organize and get together, you're going to have rocks. That is a simple sequence that you find from an element to a rock as such. As far as the groups of minerals are concerned, particularly as far as the surface is concerned, we saw earlier that silica is going to be an important component. So silicates is one of the most abundantly found minerals on the surface. Okay, they are going to be found in the rocks as well. Then you're going to have carbonates, carbonate, CaCO3. You're going to have sulfides. So you'll see that and these compounds and these organizations of minerals are going to be not equally distributed throughout the world. So, for example, when I'm speaking about sulfides, where do you find sulfur? You're going to find sulfur when you have, rather, where you have volcanic eruptions. So, sulfide rocks or rocks having groups of sulfides is going to be basically near volcanic provinces, okay, where you have active volcanic happenings. It's there that you're going to have it happening. And then you have various metals as such, and you have so much of oxygen, so these metals are going to oxidize, and then you're going to have minerals which are called as metallic oxides. So four major groups of minerals that you will find in rocks are silicates because of silica, you have carbonates, you have sulfides, and you have metal oxides. Of these, metal oxides are very commercially important because they yield us a lot of ores also. Not that the others are not, but the most commercially exploited rocks as of today are those which come from the group of metallic oxides as such. Okay, with this explanation, let us go into uh, the igneous rocks. Okay, the primary, they are called as the primary rocks basically because it is believed that these are the first of the rocks to have been formed. As a consequence, igneous are also called as primary. Now, why they are called as igneous comes from the original term ignis, which comes from fire. Okay, so this is okay, and because these are formed out of the magma that comes from the interior of the earth, they are at times also referred to as magmatic rocks as such. I'm sorry if you are not able to read through the text as such, but I would be posting this, or you could have it on SlideShare also. Search for this title on SlideShare, and you could have this. You could download this for yourselves also. Okay, this is available, as I said, on SlideShare, and it's free, freely downloaded. Okay, so the igneous rocks are those which have solidified from molten condition, molten magma as such. Okay, now the lava is going to be when the magma transforms into, or it moves onto the surface as such, we call it as extrusive. Okay, because it has come on the exterior, it has come on the surface of the earth, and that is why this is called as extrusive lava. And the rocks which are going to be solidified out of extrusive lava is going to be called as extrusive rocks as such. Okay. On the other hand, you'll see that when this molten material it solidifies, it enters the layers within, and it solidifies there itself. These are going to be called as intrusive or injected rocks. Okay, and they it's not that they stay there all the time basically, because it could be due to plate tectonics, it could be due to isostasy. Okay, what is in the interior could gradually come up as such, and what is intrusive at one particular point of time would come up as extrusive rock or extrusive rocks also. Okay, so the extrusive rocks are erupted to the surface, and the intrusive rocks are erupted into the crust. Okay, so that is the difference between an extrusive rock and the intrusive rock as such. Intrusive rocks are further classified into two. Intrusive rocks which are going to be very deep are going to be called as plutonic rocks, and intrusive rocks which are not on the surface but just below the surface. Now, when I say just below the surface, it could be a few tens of meters, and when I say very deep, it could be a few kilometers down into the Earth's crust as such. So, just beneath the surface, you're going to be called as the hyperbasal rock. Hyperbasal. Okay, hyperbasal is a word which comes from abyssal. Okay, abyssal is very deep. Hyper is halfway deep. So hyperbasal rocks. This is how you remember. Hyperbasal is just beneath the surface. Plutonic is much deeper. Both of them are intrusive rocks. Rocks which solidify on the surface are going to be called as extrusive rocks. All these together are igneous rocks, also called as primary rocks, also called as magmatic rocks. The volume of extrusive rocks erupted annually by volcanoes varies with plate tectonic setting. Extrusive rocks are produced in the following proportions, where you have divergent boundary. That means where the plates are moving or they are pushed away from each other. Obviously, you have a lot of volcanic activity. So the highest percentage of igneous rocks are being formed along a divergent boundary. That's around 73% of it. When you're going to have convergence, what happens is one of the plates is going to go down, and when it goes down here, it is going to melt, and when it melts, it is going to come up again as an volcanic eruption. So this process is very less when you compare it to a divergent boundary. So it accounts to only 15%. And then a hotspot like say the Hawaiian hotspot as such, it contributes to around 12% as rocks as such. Extrusive rocks, when are exposed to air, they lose most of their gases, which produce slaggy, cindery surfaces, vesicularity, and other characteristic structures. Rapid cooling indicated by fine-grained and frequent presence of a glassy surface as such. Intrusive rocks rarely show vesicularity, basically because the pressure within the surface does not allow gas to be trapped as such. Okay, and neither are they in contact with the gases around, so they may not contain glassy matter in this. Okay, vesicularity is basically holes. Now, vesicular is basically a tube. Okay, sometimes it may so happen that the gas is somewhere deep and it takes a long time to come to the surface as far as an extrusive rock is concerned. So vesicles are tubes through which gases rise up. Now this all happens when it's going to be molten, it's going to be very pasty as such. Small amounts of gas get trapped in the form of bubbles and they stay there. On a larger amount of gas could run through vesicles as such. So neither vesicles, neither the glassy matter is seen as far as intrusive rocks are concerned. Okay, let me see if we are missing out on anything. Yeah, rapid cooling, sorry, they alter the adjacent rocks on all sides. In lavas, only a slight amount of induration in or baking is seen as such. So that is as far as igneous rocks are concerned. What are the main characteristics of igneous rocks? We're going to come back to knowing the igneous rocks tomorrow. But the major characteristics of igneous rocks are they're classified through texture. Okay, one, that's how fast have they cooled. Obviously, the major classification is intrusive and extrusive. Intrusive is going to cool very, very slow. Extrusive, sorry, is going to cool very, very fast. So the rate of cooling will decide the rate of chemical reactions, and the rate of chemical reactions will decide mineralizations. And that is why within igneous, you're going to have a variety of igneous rocks as such. And you'll see that these minerals are going to have of different color as such. Now, on a very broad scale, the heavier rocks are darker in color, and the lighter rocks, say granite is lighter in color, basalt is very heavy and it's dark as such. You'll see that igneous rocks normally is made up of two or more minerals as such. Because the third thing is that because all of this happens at a very high temperature, you'll see that fossils in the form of leaves fossilized or even bones fossilized as such, any organic matter gets burnt off. So invariably, okay, 99.99%, you'll see that igneous rocks will not have fossils in them as such. Then further, you'll see that unlike metamorphic rocks, unlike sedimentary rocks, you'll see that they don't have layering as such. Okay, they will not erupt in layer. They will not develop in layers as such. You will have a lump of igneous rock, okay, which is basically a solidified molten material of some point of time in its deep history, geological history as such. But there could be a misunderstanding. Okay, you'll see that if you have what is called as a fissure eruption, like the Sahyadris as such. If you have been to Panchgani, or if you have been to Mahabaleshwar, or any of these, okay, if you have been to Kalsubai, okay, if you look at the Sahyadri range just opposite to it, opposite to where you are standing, you could see these layers. Now these layers are layers due to timing, okay, in the sense that we all know that the Sahyadris have formed out of fissure eruption. So a huge eruption took place and a thick layer of a few meters was formed
at a particular point of time, and then there was silence. Okay, and then a few thousands of years passed by, and then you had another eruption as such. So you have one layer which is now covered with another layer as such. So it's temporal layering. It's not the layers do not form at one particular point of time. The layers are separated by, I would say, um, thousands of years, if not millions, if thousands of years at least as such. That layering is not called as layering. Layering is when you go into formation, the rock goes into formation, do you have layers? That type of layers are seen in sedimentary, and that is what differentiates or is a main characteristic of an igneous rock, that you don't have layers in those rocks as such. Okay, then because they are formed out of conditions which are of very high temperature, high pressure. Okay, you'll see that once they are formed, you'll see that they rarely react with acids as such. Acids in the sense, you don't have acids like you have them in your chemistry labs in nature as such, but you have very mild acids as such. Now, why this point is here, this is more to do with sedimentary rocks which react with acids as such. So these rocks, that's the igneous rocks, they don't or very rarely react with acids as such, and particularly when the acids are as low as the carbonic acid, which forms when you have a lot of carbon dioxide in the air, and when the condensation of water vapor takes place. In that, what happens is the water reacts with the carbon dioxide and forms a very mild carbonic acid, and in fact that is called as acid rains at points. And you'll see that some rocks get corroded because of this acid rain as far as color is concerned. You don't have a huge variety as such, but you have that glassiness, and you have that polish in that, natural polish in them. They can be light colored, or they can be from light colored to dark colored. As I said, more the density, darker the color; less the density, light the color as such. They can be fine grained or coarse grained or glassy. Fine grained is basically it depends on the cooling rate. If they cool very fast, they form fine grained. But it's when they cool very slowly, very slowly, and this type of cooling occurs when the cooling is into the subsurface layers as such. Then you have very good coarse grained igneous rocks as such. Or you could have glassy also, and this comes out of a lot of reactions that happen with gases or other agents of erosion, and so on and so forth. And another characteristic, the last one to say so, of igneous rocks is the fact that they are resistant to weathering. Okay, now what is weathering? We are going to follow this up with this topic up with weathering as such. They are very resistant to weathering. It's a type of in situ erosion as such. Okay, they don't weather away. Okay, and that's why you'll see that you'll find rocks of igneous rocks lying here and there in on the topography, just like you saw that in when I was giving you the earlier. See, this is an igneous rock. Okay, without doubt, this is an igneous rock. So it stays there in the topography for a significant period of time, basically because they don't get eroded very fast. Not that they don't get eroded, they do get eroded, but the speed at which they get eroded is much slower, particularly when you compare them to sedimentary rocks as such. Okay, now you'll see that when we speak about igneous rocks, we spoke about their color and texture and so on and so forth. Okay, so you'll see that when you have very fast cooling as such, the surface gets shiny as such towards the right side. You'll see here, yeah, towards this side. Okay, you'll see that we have a very shiny type of a thing, but it is very dark in color. Okay, and that's called as an obsidian. Okay, a glassy dark rock is going to be called as an obsidian, and fine grained, that's cooling very fast, fine grained rock is going to be called as rhyolite, rhyolite. And of course granite is something which is cooling very slowly, and that's why the grains are coarser, and that is how on a major basis you find these rocks arranging themselves as such. How to get igneous rocks? You have melting material, cooling magma, explosive volcanism. Okay, you'll see that that is basically made up of a lot of, if the cooling magma is very slow, you'll have very less number of gaps in between them. On the other hand, you'll see that you'll have hollows and holes here. That's basically because of explosion. Uh, okay, there is a point that Akshata has brought up. I'll come back to that in how to get igneous rocks. Okay, you'll see that this type of igneous rock is got from the lower reaches. Okay, and this type of rocks, I think they'll show it in the next. Yeah, you get them on the upper reaches as such. Okay, exploding up a lot of material here, and that is why you'll have gas pockets, and the gas is released, but then the hollows stay there as far as these rocks are concerned. Okay, how to get igneous rocks further? Can you see the big differences in these two rocks? Yes, obviously these are very coarse grained and with minimum amount of gaps, but the right side is having huge hollows in them as such. Okay, now many people have studied these interiors, and you find them that the intrusive rocks are known by say how and where they arrange themselves as such. Okay, now we can start either way. Okay, from the bottom all the way to the top as such, or from the top to the bottom as such. Remember that there's going to be one time, because of isostasy that we have learned last time, that all that is below is going to come up at some point of time. Okay, now let's start from the base. Okay, this is very low here down. Slow cooling and large crystals grow. These are called as intrusive igneous rocks. These will be called as these are the plutonic type of rocks, let me tell you. Okay, the source from where the basic source from where I'll just try to make it larger for you. The source from where the molten material comes, okay, is basically way down deep, and if it solidifies on this way, huge material, it could be a few hundreds of square kilometers at a point of time. This is going to be called as the batholith. This is called as the batholith. Okay, and then you may have vertical structures coming out of these. These are called as dikes, D-Y-K-E-S. These are called as dikes as such. Horizontal outlets from this is going to be called as sills as such, S-I-L-L. Horizontal ones are going to be called as sills as such. And then sometimes you'll see that the material, that's the magma material, gets pushed in between layers as such. These are called as plutons when they are huge bulbs. Okay, they are going to be called as plutons. Plutons are here. These are plutons, and this is a laccolith. The difference between a pluton and a laccolith is the pluton forms a bag-like structure, but the laccolith is a lens-like structure. It forms a lens. It spreads. Okay, now it is not necessary. Yeah, one of these things is how the layers beneath the surface are, but this also depends on how the quality of the lava is, or the magma is. If the magma is pasty, very very pasty, thick, viscous as such, then it will gather as a bulb. Okay, it will not flow. But then if it tends to get pasty, it gets a bit more fluid. Okay, and it spreads in a peculiar shape. That's a lens shape as such. We're going to call it as magma as such. Okay, then you see that as far as the top ones, okay, the extrusive ones are concerned, if it's obviously leads to very fast cooling, and you'll see that you're going to have layers of flows. Let me tell you, this is not layers of igneous rocks. These are layers of flows. Just as I said, the formation of the Sahyadris. Okay, these are layers of flows as such. This is normally the intrusive and extrusive features as rocks as such. This is another picture of this, the same thing. Okay, you have huge stores of them in the batholiths, and then you have the vertical dikes, and you have the horizontal sills everywhere. You're going to have laccolith. Now this laccolith has come up, and because it has come up, you'll see that it now shows as a hill, and a flat topped hill is going to be called as a lava capped plateau here as such. Okay, these are the volcanic rocks tops here. uh, Here you're going to have the volcanic tops here. This is the lava capped plateau. Okay. Okay, the Grand Canyon is something like this in the US. And then you have veins. Okay, when very small tender ones, lava flows into the nearby, flows between, into, or through the lavas. Okay, just to repeat it, these veins will flow between. Okay, they will flow between, or they will flow into, or they will flow through the rocks. Okay, so these could be formation of veins as such. Gold many a times is found in veins. Okay, that's why these igneous veins are very important as such. Let us see if we have, yeah, this is the igneous classification. This classification is based on um, the from left to right, okay, the texture of the grains. Okay, we'll read into this tomorrow. I'll get the original thing that I have on my computer, and so that we can say zoom into or zoom out of this as such. Okay, then based on the amount of silica, based on the mineralogical composition, and based on the mode of occurrence also. So these are the various ways in which we tend to classify igneous rocks. Now this slide has been made by me. I had invested a significant amount of time for this, and that's why you can find my name down here and copyrighted as such. Okay, I've worked through these three different types of rocks, and thus these are the different types of igneous rocks. So that was the last slide. What I'll do is I'll stop here for the day, and let us see if I have any questions from your side. I'll stop presenting. Okay, so that is what we had to do about the igneous rocks as such. Now, Akshata has a question. She says that this, sir, I'm doubtful about the authenticity of the slide showing the composition of the Earth's crust and the oceans, because the percentages are shown on the slide didn't sum up to 100. As I said, geography is not pure mathematics. First thing, these are approximated numbers. Though we are speaking in terms of percentages, even a small point percentage of any element could yield you thousands and thousands of tons of that particular material. Now, just see, gold does not rank there, silver does not rank there, but say, to be fair to all countries, you have and different countries as such. Majority of the countries have tons and tons of gold, which does not rank. So you can imagine what is the percentage of the other. When we say oxygen is 47% in the crust, it would simply mean a huge amount of oxygen there as such. It should not be that arithmetic. We should not get that arithmetic about it, because with that volume of these elements, it is very difficult to actually quantify them, and so we put them in approximate percentages as such. Earth's crust, I'm sure. Oceans, I did not verify this, basically because I got this slide from Google web page. So this could be half of the Earth is made up of feldspar. Where did you read that? I don't know, Harshal. You say half of the Earth's crust is made up of feldspar. I would not agree to that. This needs to be confirmed. I would like to know the reference from where this comes from. Yes, feldspar is one of the most commonly found igneous material, but whether it constitutes half of the Earth's surface is difficult, basically because when we are referring to the surface, I'm not referring to the crust. Surface, let me tell you that 75% of the surface, I again repeat, it's not the crust. 75% of the Earth's surface is covered with sedimentary rocks. So, let me tell you that scientists make these statements. It's very, again, when I say half, have I found out the other half is an important aspect. Have I been in a position to quantify the other half as such? It's only in that case that we would say that half of the Earth's crust is made up of feldspar. Um, I'm not very sure. Let me confirm it, and I'll come back tomorrow. If you have answers to these, you could post it on our the WhatsApp group also as such. So that's all for the first lecture of the new year. We have started with rocks for the new year, and we have partially finished. A few things about the igneous rocks still remain. I need to explain you the whole classification chart. I will see that I get my individual PPT and not the one. I thought that the one posted on the slide share could help me as such. I could have downloaded it, but then that's again a PDF format. I will get the PPT format of it tomorrow, and we'll go into the details of that. If you have any more questions, you could just post these questions, and if I'm able to answer, I would answer them for you all. If not, I'll come back with the answers. I'll try to come back with the answers tomorrow. If you don't have any more questions as such, then let us call it a day. I suppose you would be having your other lectures also. So that's all for today. Once again, I wish you all a very happy new year. Let's hope that this year is very healthy for all of humanity, all through the globe as such, and of course Indians. Also, let us hope that we get vaccinated and we stay away from this deadly virus that we invited, called as COVID-19, which wrecked the planet throughout the year of 2020. That's all for the day. We'll stop here. I'm ending my broadcast right now.